Hello students, in this lecture series we'll start another chapter, ethers. Ethers are the organic compound containing oxygen atom attached to two hydrocarbons. Functional group of ether is functional group of ether is functional group of ether is dash O dash. Here both the sides you are having hydrocarbons and they are functional isomers of alcohols. Since ethers can be obtained by the elimination of water from two molecules of alcohol, they are also called as anhydrides of alcohol. Suppose this is one molecule of alcohol, ROH. This is another molecule of alcohol, yes, ROH. Eliminate a molecule of water like this. You will left with ROR plus H2O. Here these two are hydrocarbons. These two are hydrocarbons. This is the functional group of ether. So these ethers are obtained. Ethers are obtained by the elimination of a molecule of water. So they are called as anhydrides of alcohol. So ethers are called as anhydrides of alcohol. And their ethers are represented by general formula. Ethers are represented by general formula. ROR dash, where R and R dash may be alkyl groups or aryl groups, or R and R dash are the alkyl groups or aryl groups. Alkyl groups or aryl groups. Example, CH3OCH3. This is methoxymethane. CH4 is methane. OCH3 is methoxy group. So methoxy. One hydrogen atom is replaced by methoxy group and this is parent compound methane. So methoxymethane or dimethyl ether. Another name is dimethyl ether. This is another example, ethoxyethane. This is C2H6 is ethane. One hydrogen atom is replaced by ethoxy group. So ethoxyethane. Next, let us see the types of ethers. Ethers are of two types. One is symmetrical ethers, another is unsymmetrical ethers. Symmetrical ethers are those ethers which contain similar groups on either side of oxygen. They are represented by general formula ROR. Examples. Yes, these are the same example here. As they have general formula ROR, it means both are same. Here the hydrocarbons attached to the oxygen atoms are same. Example, CH3OCH3, methoxymethane. Here the groups attached to the oxygen atoms are similar. C2H5, OC2H5. Ethoxyethane. These are examples for symmetrical ethers. The second one, unsymmetrical ethers. These contain different groups on either side of oxygen. These contain different groups on either side of oxygen. They have the general formula ROR dash. They have the general formula R O R dash. R O R dash, where R and R dash are different. R and R dash are different. Example where R and R dash are different. Let us see the example. CH3OC2H5. CH3OC2H5. Methoxyethane. This is methoxyethane. Methoxyethane. Second example, CH3O CH2 CH2 CH3. This is methoxypropane. Methoxypropane. Now we'll discuss preparation of ether, that is by the dehydration of alcohols. When excess of alcohols are heated to 413 Kelvin in the presence of concentrated sulfuric acid, ethers are formed. Now let us write the general reaction for this particular preparation. ROH plus HOR. These two represents alcohol. Excess of alcohol is heated with sulfuric acid, small amount of sulfuric acid, H2SO4, at 413 Kelvin. You are going to get ether, ROR plus H2O. This represents alcohol. This is also alcohol. This is ether. Excess of alcohols are heated at 413 Kelvin in the presence of concentrated sulfuric acid. Ethers are formed. Here water molecule is eliminated during this reaction, so this is called as dehydration reaction. This is called as dehydration reaction. Now let us see the example. When excess of ethyl alcohol is heated with concentrated sulfuric acid to 413 Kelvin, diethyl ether is formed. Write this reaction: C2H5OH, C2H5OH plus HOC2H5 in the presence of concentrated sulfuric acid at 413 Kelvin. Eliminate a molecule of water. Eliminate a molecule of water like this. You are going to get C2H5O, C2H5O plus H2O. Excess of ethyl alcohol when heated to 413 Kelvin in the presence of concentrated sulfuric acid, diethyl ether is found. Now let us discuss mechanism of this particular conversion. Conversion of ethyl alcohol into diethyl ether is explained in 3 steps. First step is protonation of alcohol. In first step, the catalyst sulfuric acid protonates the alcohol to form a cation. First, sulfuric acid undergoes the dissociation to produce H plus ion and HSO4 minus ion. The H plus ion produced during this conversion converts or adds to the molecule of ethyl alcohol to form protonated alcohol, that is ethyl oxonium ion. Now let's discuss the reaction. H2SO4 undergoes ionization to form H plus ion and HSO4 minus ion. Then this H plus produced protonates alcohol CH3 CH2OH. H plus adds to a molecule of alcohol to form ethyl oxonium ion, a cation. CH2OH2 plus this is ethyl oxonium ion, ethyl oxonium ion. This is a cation. Now let us see second step. In step 2, the unprotonated alcohol which is to which H plus is not added, that is called as, this is unprotonated alcohol, attacks the carbon containing oxygen atom of the cation form, to give oxonium ion and water molecule. Now let us discuss the reaction CH3 CH2 which this is unprotonated alcohol, means H plus is not added to this. As excess of ethyl alcohol is taken, all ethyl alcohol molecule doesn't form ethyl oxonium ion, some remains as alcohol only. This is added to the carbon atom of ethyl oxonium ion. This is CH2OH2 plus. OH2 plus. Here this oxygen atom, the unprotonated alcohol, attacks the carbon containing oxygen atom of the cation, to form oxonium ion and a molecule of water. This oxygen attacks this carbon atom, then this bond moves towards this molecule. You are going to get oxonium ion, CH3CH2 OH, CH3OH. This carries positive charge because this is attached to CH2CH3 plus H2O. This is known as oxonium ion. This is oxonium ion. In the third step, already we have discussed, since excess of ethyl alcohol is taken, all molecules does not form ethyl oxonium ion, so unprotonated alcohol is available. The alcohol which is not added to this H plus, and that is available for the attack to the carbocation, attack to the ethyl oxonium ion to form oxonium ion. In step 3, the oxonium ion formed loses a proton. It loses this proton to form final product, that is ether, diethyl ether. Now we'll write this reaction. Oxonium ion formed in step 2 loses a proton, CH2, this is CH3, CH2, OH, CH2, CH3. It loses a proton like this. Movement of bonded peripheral proton takes place like this. H comes out as H plus. So you are going to get CH3, CH2, OCH2, CH3 plus this H plus ion. This is diethyl ether. This is mechanism of conversion of ethyl alcohol into diethyl ether, alcohol into ether. Now we'll discuss Williamson's ether synthesis. Okay. First, alkyl halides are heated with alkyl halides are heated with sodium salt of alcohol. Sodium salt of alcohol, heat it in alcoholic media. In the presence of alcohol, alkyl halides when heated with sodium salt of alcohol, in the presence of alcohol, ethers are formed. You are going to get ethers are formed. This reaction is known as Williamson's ether synthesis. Now I'll write the general reaction. RONA. This is sodium salt of alcohol. Plus alkyl halide. General formula is XR. This is alkyl halide. Heat it in the presence of alcohol. You are going to get ether. R dash plus NaX. This is ether. This is general reaction for Williamson's ether synthesis. Example: when ethyl bromide is heated with alcoholic solution of sodium ethoxide, diethyl ether is formed. Ether is formed. This reaction known as Williamson's ether synthesis. C2H5ONA, sodium salt of ethyl alcohol. This is nothing but sodium ethoxide. Is heated with ethyl bromide, BrC2H5, ethyl bromide. Heat it in the presence of alcohol, eliminate a molecule of sodium bromide. You are going to get C2H5 plus NaBr, diethyl ether. This reaction is known as Williamson's ether synthesis. Now let us see note here. Yes, here the reaction takes place by SN2 mechanism. This conversion takes place through SN2 mechanism, means inversion of configuration takes place. Since nucleophilic attack takes place on the alkyl halide, the alkyl halide should be preferably primary, but the alkoxide ion can have the tertiary group. Now let us see, as the reaction takes place by SN2 mechanism, since nucleophilic attack takes place on the alkyl halide should be primary, but the alkoxide can have a tertiary group. Now let us see what happens if primary alkyl halide is taken, what happens if tertiary alkyl halide is taken. We'll discuss two more examples in this regard. Now let us see one example. For the preparation of tertiary butyl ethyl ether, ethyl chloride and sodium salt of tertiary butyl alcohol is taken and not vice versa. Okay, here for the preparation of tertiary butyl alcohol, you cannot take sodium ethoxide, alkyl halide, that is sodium ethoxide, and sodium salt of the tertiary butyl chloride. If it is reversed, in place of ethyl chloride, if sodium ethoxide is taken, in place of sodium salt of tertiary butyl alcohol, if tertiary butyl chloride is taken, you will not end with the ether. We'll discuss both the reactions now. Here first, sodium salt of tertiary butyl alcohol, that is CH3, CCH3, CH3, ONA. This is sodium salt of tertiary butyl alcohol plus sodium salt of tertiary butyl alcohol plus CH3, CH2Cl, ethyl chloride. This is ethyl chloride. Eliminate a molecule of sodium chloride here. CH3, CCH3, CH3, OCH2, CH3, OCH2, CH3 plus NaCl. You are going to get tertiary butyl. This is tertiary butyl ether, tertiary butyl ethyl ether, tertiary butyl ethyl ether, tertiary butyl ethyl ether, tertiary butyl ethyl ether. Now let us see what happens if sodium salt of ethyl alcohol and tertiary butyl chloride is there. What will be the product? When alkyl halide uses tertiary, and alkoxide ion cannot act as nucleophile due to steric hindrance, but acts as a base, hence abstracts a proton from adjacent carbon atom, resulting formation of an alkene. When alkyl halide used is tertiary, the alkoxide ion cannot act as a nucleophile due to steric hindrance, but act as a base and hence abstracts a proton from adjacent carbon atom, resulting in the formation of alkene. Now let us see one example. When tertiary butyl chloride is heated with sodium ethoxide, you are not going to get ether. Instead, you are going to get an alkene, that is 2-methyl prop-1ene, 2-methyl 1-propene. Ether is not found because we have interchanged this tertiary alkyl halide and we are going to take primary, the sodium salt of primary alcohol. Let us see that reaction. This is sodium ethoxide, reacts with tertiary butyl chloride. This is tertiary butyl chloride. Here, this oxygen atom attacks this hydrogen. This takes this hydrogen. Then this bonded pair of electrons concentrate here, and Cl goes out along with the bonded pair of electrons. Will end with an alkene. CH3, C double bond CH2, CH3, CH3, C, CH3, CH3, C, CH3, double bond CH2, double bond CH2 plus CH3 CH2OH, CH3 CH2OH plus NaCl plus NaCl. This is 2-methyl 1-propene. Okay, this is if the alkyl halide and sodium salt of alcohol are interchanged, you will never get an ether, but instead you are going to get an alkene. In the case of primary alkyl halides, in Williamson's ether synthesis, if primary alkyl halide is used, or in the case of primary alkyl halide, if primary alkyl halide is used, substitution predominates, means substitution takes place. Substitution predominates over elimination. Means in Williamson's synthesis, the substitution takes place through SN2 mechanism. So if primary alkyl halide is used, then substitution takes place rather than elimination. If tertiary alkyl halide is used, elimination predominates. Rather than the substitution. Elimination predominates over substitution. Hence we will end with an alkene if tertiary alkyl halide is used. And this Williamson's ether synthesis is also used to prepare aromatic ethers. Example, we can prepare aromatic ethers starting from by using Williamson's ether synthesis. When sodium phenate is heated with sodium phenate is heated with methyl iodide, this is primary halide. Just heat it, you are going to get methoxybenzene, OCH3, methoxybenzene plus NaI. This is also known as anisole. Methyl phenyl ether, another name methyl phenyl ether. This is about Williamson's ether synthesis.